My background is academics. I was a professor at Boston University until some time ago. I had a lab called Neuromorphics Lab, so my background is neuroscience and artificial intelligence. And the lab has transitioned over the course of the past few years in a company called Neurala. And that's my second GTC in a month. So we started to develop a saying in Neurala, which is 1 GTC per day keeps NVIDIA at bay. And so I did my GTC for this month. So what's Neurala? It's a company that has one objective, and is to transition humankind, if you will, from a state of what we would like to have to what we have, from what we have today to what we would like to have. So many of you have seen these robots, unfortunately, mostly of them on YouTube, and we want cow-shaped robot to carry our stuff around if you are in the military, or Amazon drones to deliver our packages or to inspect pipelines, telepresence robots to follow us around, or robot that entertain us in the house. But most what we get today is still a remote control. And I call this the one-to-one ratio problem. It doesn't make any sense to have a bunch of machines if you need a human per machine to control them. Similarly, in the DoD domain, we want machines that are able to accomplish complex tasks. And the task can be, for instance, use swarms of 1,000 robots, patrol this area, secure it, and tell me if anything is wrong. What do we get today is still maybe something more that you can get in commercial space, like maybe patrol a little area and move forward or leftward, but you don't get the sort of high-level autonomy that you really want. The problem here is even more severe because to control, for instance, a large UAV, you're more into the 300 to 1 domain with hundreds of people to control a single drone. Thankfully, there is a solution to the problem, and the problem can be solved by looking into the human brain. And that's what we have been doing, and Neurala and other scientists across the planet have been doing for the past several years. So the brain is phenomenal, 100 billion neurons to after 250 trillion synapses, all packed in a little box that consumes about the power of a light bulb, which is something that NVIDIA maybe in 100 years can do. So we're still lagging behind. And the brain, by combining very simple computing elements and synapses between these computing elements, can give us all the emergent behavior that we are capable of. And the three co-founders of Neurala, Heather, Anatoly, and myself, have been studying the brain for the past 10 years. We actually started Neurala as a company to contain a patent in 2006 that we thought of to use GPUs for brain computing. So that was in the so-called BC area, or before CUDA, so way before it was easy to do. These are the things that we are looking at. That's a little example, if it places better, of the sort of technology we have been building. So this was in collaboration with NASA, and it's basically an artificial brain that drives a Mars rover-like device around a Mars environment, doing simultaneously navigation, perception, object recognition, collision avoidance, and so forth. So the whole deal is for us to shift the balance between where we are today and where we are in the future, where most of the computing power today of a main system is still in the brain of the operator, to a situation where much of the computing power will reside on the device itself and will take care of the majority of the tasks, which are low-level perception and navigation, so freeing up the brain of the operator who can control multiple devices at once. So what does this AI look like? And it looks like a little different than maybe what you thought. And you've seen examples in prior talks of object recognition technology and navigation technology. Truthfully, to get a machine to be really useful and navigate, for instance, with humans in the field, you need a brain. So you need a variety of these brain areas, from navigation to vision to motor control, planning, sensing, and so forth, all connected and work at unison or in coordination to solve a particular task. So each one of these boxes here, a map or a pose estimate and so forth, it's what people call today deep networks, that before were called neural networks before they changed name. So what's the difference between these deep networks and traditional AI, where traditional AI can be, for instance, a decision tree or a more classical approach? Well, AI is not easy to use, right? Still, despite all the effort, they're non-transparent systems. So they are not transparent, so you don't know exactly what's going on, right? So why, and you don't know that from people, right? So why does a person like red? I don't know, I cannot open the brain and see why do you like red. He just likes red. For the same principle, sometimes AI systems based on neural networks are opaque. But when you look at performance, when you look at robustness, and when you look at the ability to adapt, neural networks are superior. And that lies mostly because their ability to adapt, because they are based on learning. So they're based on examples versus traditional AI, they're based on brute force methods. So brain-inspired versus traditional AI, the balance has shifted. So today, the best system in a variety of fields, from object recognition, written language competitions, traffic sign competition, medical imaging, you have neural networks beating on a regular basis all other systems, sometimes achieving superhuman performance, which means if you have a human and a machine, the machine is going to beat the human. And that's a specific example that I took from the MNIST dataset. It's handwritten digit recognition, so the sort of algorithms that will read your check, handwritten check when you deposit it. All the first 5 positions are neural networks today. So let me give you an example of what we have done, for instance, with neural networks. So that's an example of the Mars rover brain, which we have taken and put in a car in collaboration with a tier 1 automotive manufacturer to basically use example, learning by example, to teach a car to avoid pedestrians and other vehicles and other obstacles. After about 100,000 iterations, the car, equipped only with a monocular single camera, so the same camera you have in your cell phone, and the GPU, was able to learn to avoid the collisions just by sheer number of examples. That's another example of a technology that is actually going to be deployed and present in consumer drones and in automotive. Consumer drones at the end of this year, and automotive hopefully a little later, because automotive is fairly slow. And this is just the visual system of the algorithm I just showed you before of the self-driving car that recognizes object of interest on the road for the purpose of collision avoidance or autonomous warning system. And that runs at about 15 frames per second on an NVIDIA TX1. So this stuff is actually coming to market as we speak, and these are commercial deals that we already signed. So in terms of DAD and unmanned system, one of the important issues is communication bandwidth. So you don't want to communicate everything that your machine is doing, like all the raw sensory data and so forth. So that's an example of the NASA project I just mentioned, where the task is you don't have GPS connection, you have only local computation, and now your task is explore an area, avoid bumping into things, which is mostly rocks on Mars, perceive these rocks, put them in an environment, go around and come back to your starting position, all locally using a single GPU and a single very cheap monocular camera. So the goal here was to be extremely local, extremely cheap, and not connected. So that's an example of the visual system of this Mars rover brain. And what you can see it does, it automatically finds the object, points to it, sort of like a human moves his gaze or his center of attention, segment the object, classifies it, and puts in a sort of a map that tells the robot, I see you, and I see you there. So now let's put it all together, and that's an example of a full brain system of the kind I showed you before that coordinates autonomous perception, navigation, collision avoidance, all in a single package running on a NVIDIA GPU with the only sensor as a single camera, so no LiDAR and no active sensor. So that's the example of the dead reckoning algorithm, or the ability of the robot to go around and come back to the starting position, at the same time classify an object and putting them in a map. And the algorithm has to be able to find its way back to the starting position. So right, when you start a mission, you have to be able to classify the object, but also come back to your starting position without any GPS information or any active sensors. At the same time, effective navigation requires you to avoid collisions. You have a single camera, so what we have developed is a safe and unsafe algorithm that tells in real time this is a safe, traversable area, whereas this is an obstacle. And again, you cannot have tricks, no binocular vision and no active sensors. So that's another example of how you can reduce the communication bandwidth and not broadcast the whole image, but just what you need. This is a demonstration we have done with Aerotronics at the prior GTC that was in Amsterdam, where we have put our algorithm on a drone designed by Aerotronics in collaboration with NVIDIA for the purpose of analyzing locally on the drone the video stream. In this particular case, the objective was to find, classify antennas, rust, serial numbers in telecommunication sort of devices, like a telecom antenna. So the key here is that you don't have to broadcast the whole image. You just broadcast the very lightweight information that is semantically charged. So it has a semantic value to it. Similar project, again, demonstrated last month at GTC Amsterdam, this time in collaboration with NVIDIA and Squadron System, which is a French drone manufacturer, also known for Exoplus, which was the drone that followed you around. And the goal here is to automate the process of counting items in a logistic environment. So in order to do warehouse maintenance or warehouse closing, what you need to do is to close the warehouse for a week. And have labor, employees go up the shelves, potentially with the danger of falling down. So the drone automates this process by flying and automatically recognizing items, for instance, in boxes, counting them for you, and then broadcasting the net result of the counting back to the operator. A big issue, both in defense and also other commercial applications, is can we trust AI? Is AI accountable? And the trust is broken, right? At the current stage, there are a lack of standards, in particular in defense-related application. AI is hard to understand, so it's not easily explainable. So you cannot explain what the system does very, very well. It's also very hard to forecast every potential combination of environmental conditions, right? So right now you see me under this illumination, I can be in the dark, I can be tilted. There is a so-called combinatorial explosion of different situations that the system can face. Therefore, it's hard to sort of certify a system. So as a consequence, systems get deployed without much certification. So that's the bad part. I think there is hope. If the fundamental equation AI system equals human, then we do have a series of procedures that we use with human beings to certify general knowledge. My kids go to school, they get infused general knowledge and they get tested. Motor skills and complex procedures. So we have a way to train them and then to test them. So this is a little example of what we do in Neurala to do this. So this is an example of an object recognition application running on a cell phone. So what we do is we build the requirements with the customer. We create a set of goals or trust. For instance, this needs to do 90% correct on 150 objects and run under 2 seconds. All right, so that's the target. Then we develop the algorithm. We test in two sorts of scenarios. One are synthetic data sets that are available, the Caltech 100 and so forth. And then in virtual environment. Do not underestimate the power of virtual environments, because that's the next step between a synthetic algorithm and reality. Then if we pass the test, we go to an alpha test within the company, and if we pass the alpha test without redesigning, then we go to a beta test at the customer site. So that's the best we can do today. I know it's not perfect, but it's better than zero, or better than just deploying and see what happens. So that's an example of how we went from a synthetic test to virtual environment to real environment. So this is a project we did with NASA, NASA Langley in Virginia, where we were trained to create a system running again on GPU to avoid collision in midair. Problem, there is not a data set of collision in midair, right? Thankfully. So we had to build it, and we built it in a Microsoft Flight Simulator. So we trained it, and then we deployed into a real system flown by NASA into their facility. So it kind of worked, and now we are at the next step, which is we are going into a real environment with the little caveat that this customer doesn't want us to avoid collision, but to cause them. Right? So this is a drone interceptor project, where all we are doing is we are using our algorithm to scout other drones in the airspace, and then we are powering the system to sort of a projectile kind of device to capture the drone and take it down. So unexpected consequences of sense and avoid. So capabilities, what capabilities are possible in commodity hardware? And I have a personal story. So much of my activity was linked at a certain point with a program called DARPA Synapse, which was basically the attempt to build, I call it a Terminator brain for lack of a better word, but a very complicated and a novel chip based on memoristic devices, which are this sort of exotic memory that were promising to replace basically human synapses in silico. And at a certain point in the project, we started to use GPU back in 2008. And they say, well, until the system is built, we're going to use GPUs. And the system was never built in the form factor and the power requirements that was achievable according to DARPA. So we kept using GPUs. But I got a little wary and worried about exotic chips. My suggestion to the community has always been use existing hardware. AI is mainly a software problem as of now. Build the algorithm, let the hardware evolve, following, for instance, companies like NVIDIA, but also others that are playing in the field. And NVIDIA is doing pretty well. This is a slide from the NVIDIA people. And the beautiful thing here is that we and Neurala have to do virtually nothing, apart from keeping updated the SDK and so forth. But the next generation of the embedded platform, which we are going to have deployed in customer at the end of 2016, will have almost twice the SGEM, or the computing power per watt, of the prior generation. So we can put twice the brain, or tune up or increase the resolution of our current brain at no particular cost for us. Finally, a little note on integration of artificial intelligence in unmanned system. And there is a tendency that I have noticed in my little history working with governmental agencies of considering AI as a hardware problem. Going back to DARPA Synapse, but also seeing current efforts to build hardware. So this turns out to be, I think, the wrong approach. I believe that artificial intelligence is a software or an algorithm problem. And there is a way in which the government or governmental agency can quickly iterate on algorithms and AI application by exploiting the price of commodity devices that are today on the market. So for instance, today you can do an AI drone project using a $1,000 DJI, equally cheap Jetson development board, and a cell phone as the controller. And so you're shifting the balance between a hardware project that is going to cost tens of millions of dollars and last a number of years into a software project in which you're quickly iterating on the algorithm, deploying in the field almost immediately, and then iterating continuously and improving the algorithm. And there is another benefit, right? You're going to know pretty quickly whether you failed or not, and that has a price tag by itself. So in summary, I'd like to take questions, but I think that AI is finally here. There's been a convergence of technology and algorithm that a prior speaker like Jesse, for instance, pointed to. Big Bang in 2012 with AlexNet. I believe the Big Bang was actually a little earlier when GPU became programmable, back in the early 2006 and 7, though we had to do it in pixel assembly and not in CUDA. But that plus the availability of cheap bodies or cheap robots that are drones and toys and other devices, it made it possible today to start to see this stuff deployed. And it's really exciting time. Happy to take questions if you guys have any. Yeah, so the problem, I think, is going to be solved by the applications where the biggest drawback of AI failing are going to be seen. So I see the two fields where this is going to happen is automotive and unmanned system for the DoD. So those two, and that's actually for the first time, I think DoD is going to take a step back or do it in collaboration with the private industry. And that's because of the tremendous effort going on in automotive today. So I believe that the solution will start to come from those two fields, and in particular automotive with the when the manufacturer are going to start to consolidate the technologies. Right now, everybody is doing it in its own backyard and in isolation. When the consolidation phase will occur, where there will be less than 100 winners, then I think they will start to share nodes and start to create standards for certifying the cars before they hit the road. Yeah, so as a matter of fact, we are currently working with an automotive manufacturer that uses LiDAR. As a historical tendency, we have shied away because focusing on just a single monocular camera has given us the edge with respect to competitors that only work with LiDAR or required other sensors. So whereas those guys are still bound to those sensors, today we are actually shipping in products that just come with a single monocular camera. So it has been a deliberate choice. And obviously, if you have stereo and a point cloud, everything is easier, right? So you have a depth plane that pop out of nothing, right? So that's actually the easy part. The hard part is to do it with a flat 640 by 480 monocular image. After lunch is hard, I know.
Okay, thanks a lot, Max.
Thank you, guys.